And there's arrays in there, there's antenna radiation, there's a whole lot, but I'm going to try to piece it together so it's seamless. Now anyway, when we talk about potentials, sort of to you that's a loose term. You don't know what you're talking about. So let me give you a clear example. You remember voltage back in the day? Well, if you had a charge, let's go statics. If you just had a charge Q, as a matter of fact, make it a distribution of charge. You had some rho L, a line charge. And you wanted the voltage in space, you could get it, right? Do y'all know that? I'm going to just write down a general integral. Please don't, you don't have to write this down. This is the way I'd like it done for me. So, in general, voltage is what? This is electrostatic voltage was an integral of rho, in this case L, dl, it's over wherever the charge exists, over 4 pi and r squared, right? And then there would be an epsilon guy here, an epsilon naught, and that would be over the volume or the length. Y'all remember that? This is real general. Now, what was nice about a voltage compared to an electric field? An electric field is a vector quantity, right? And when you did an electric field, in general, you had 3 integrals. You would have Ex, Ey, Ez, right? And it would be rho L, dl. Then there would be 4 pi r squared, right? And then there would be an AR component. Really, this would, I'll just put the AR vector and I'll cross these two out. AR vector is really R vector. It would be a vector from the point from the differential charge to the point where you wanted the E field, right? And this would be vector R. Do you all remember that? How to get the AR is really R vector over the magnitude of R, right? Well, in general, this had 3 integrations, didn't it? Y'all remember that? Back in the day, electric fields can have 3 components. In general, AR, it could have 3 vector directions, and the integrations, at least generally, got sloppy and hard. They did. So what you would do is you would take the voltage potential, and you would say that to get E, I would say it's minus the gradient of the voltage. Y'all remember that? Now, a gradient operator's derivatives, that was easy compared to these crazy integrals. And I speak from experience, because I've had this in graduate classes, I've taught it, and these integrals can get nightmarish at times for odd charge distributions. But taking a derivative of the function, especially nowadays with Mathematica and Mathcat, even your calculators do symbolic integration, or symbolic differentiation, it's not too bad. So that was the deal. So you liked voltage. You didn't like calculating E field directly. The voltage was an intermediate calculation involving a potential. Do you all follow me in this? And that says it, and this is for electrostatics, right? How many remember this stuff? Am I making sense to you? And far back, do you get this? I'm just trying to keep everybody at least somewhat interested. So now, let's talk about electrodynamics, time-varying electric fields related to antennas. So now, here we go. We're going to start, well, how did we do it with when you were exposed to voltage? Don't write this down, please. Do you remember what you had? You had a differential chunk of charge, and you say if I'm a distance away, R away, that I get a differential voltage is actually dq, and it's over 4 pi r squared. And then you would integrate that differential voltage over where the charge existed to get the total. Do you all remember doing that? Well, here's how we do it using potentials with current to get the E field. What we do is say, now you can write this down. We have a little chunk of current. I dl. Now the dl is actually the vector sense of that chunk of current. I is just the magnitude. In the book you'll have I naught, but I'm going to leave it as I in general, okay? Now if you go from the center of this thing, a distance r away, you're going to get something that's called a magnetic vector potential A. You don't need to replicate this work. This is to give you perspective. So you're going to get a magnetic vector potential A in the same direction as the differential current. And that's equal to, and in your book you'll see that, it's mu0 over 4 pi, and it's I naught here, divided by r. Actually, I put this as r squared. This is actually r. I'm sorry. It's dq over 4 pi r for voltage. Electric field would have r squared. My bad on that one, okay? And it's over r, and that's the distance here. The vector sense is just A right here, and it's in the current's direction. So it's in the direction of the current is the unit vector there. And it's equal, there's also going to be an e to the minus j beta r, and then it's dl. Now I'm going to explain some things about this. Sometimes in the book, once you write that down, remember, I can call this line out. The only thing this is, the magnitude is here. The vector direction dl I broke up into ai dl, where dl would be a scalar. In his book, he'll have dl with a vector sense and just cover that up. But it's got to have a vector sense and a differential length, okay? Now that's the differential electric field, so I didn't put this there, but this would actually be dA, just like that would be dV. The A there is called the magnetic vector potential. You're going to see in a minute this sort of goes away after I take care of a few things. Now when you have this, if you wanted the total value of A, then you would integrate this over the length of the line. And if I integrate this over the length of the line, I get the total magnetic vector potential. And by the way, until you see this actually done a few times, you don't appreciate it. Let me give you another bit of perspective. This e to the minus j beta r is a phase. I don't have to do it with a phase. I'm not going to do this here. Just pay attention to this. You don't have to write this down. But if I wanted to do it in the time domain, I wouldn't write that down. What I would do is replace this with cosine, and this would be omega minus beta r here. All right, but this would be omega, actually, I'll even get rid of this. It's just going to be omega, and it would be t minus the actual delay time for the electromagnetic energy to get from this antenna to this point. Well, that delay time will be distance r divided by the velocity of light. And I can replace that if I wanted to time it. Does that make sense, everybody? Because it takes a certain time to get there, right? So that's the r, the distance over c. Now, if we wanted to, we can expand this, and you'll follow me on this. What if I expand this? I get omega t minus r omega over c. Well, what is omega over c? It's beta, isn't it? So that, in fact, is beta r. Now, you don't have to worry about that, but that's how you get this term right here. It'll be this way in Whitworth's book. It's just a phase term that comes about from the speed of light. All right? Now, carrying on, I want you to take note that A and the current are in the same direction, always. All right? The differential current creates a differential magnetic vector potential dA in the same direction. If I had a loop of current, then I would have to get the vector components, the differential vector components at each angle and sum them. Actually, I'd have to sum them with an integral, but actually vectorially, okay? So keep that in mind. Now here's the nice thing, that's A. Remember I said it's a scalar. It's really a vector, but it has only one direction. That's the nice thing. It's effectively a scalar. Got that up, everyone? So I got this, so big deal. How do I get something of meaning that I can measure? You can't measure this. And by the way, you can only measure voltage when you have 2 points to measure it between. 100,000 volts means nothing unless it's with respect to something, usually a ground. You all follow me on that? Here, this you can't measure, no matter what. It's used as an intermediate potential to get something. And here's what you get. And I'll tell you where this is in Whitworth's book, because I know I'm going to get that question right at some point. In Stu's book, Dr. Whitworth's book, it is tab this page.
441.
Thank you. Yeah. And And the way he does it is a little confusing, I'm going to say that, at least to me. This is on page 440 and 441, but he starts with the equation I put up there is 8.35. That's this equation if you want to write it down. This is my version of it. You can look at his. It's going to get a little busy. He has a current density there, and it'll get a little harder to understand. We're doing a thin wire, just a wire. So that's A. Now, from that, and he does the rest. I want to see where he has what I'm looking for. Yeah, he has an equation 8.39. He says from this, I can get B. Now this is measurable, and B is equal to the curl of A. B you can measure, but you can observe. This is important. Y'all with me on that? That's the magnetic field. B is in what? Webers per meter squared. Remember, it's a density. It's a flux density. B is also equal to mu 0 h if it's free space. Y'all remember that? So I can say that really H is equal to 1 over mu 0 times the curl of A. Now curl is not something you guys just jump up and down about, you get to do. Curl is actually quite easy to understand and deal with for a lot of things, and you won't be doing much with it, I'm telling you. I'll show you what you need to know. But it's nice, I would never ask you to do a curl in cylindrical or spherical coordinates without the actual equations at the back of your book. And if you have your book, if you look in the back cover, one of the things you're going to see curl. You see it? And there'll be curl in Cartesian, that's the easy one, cylindrical and spherical. Y'all with me? All right, so that's H. Now, if we have H, we can get E. You with me on this? And somebody is going to say, well, how do you get E? First, we're going to assume we're in a lossless environment. Lossless region. Or that sigma is 0. If we don't do that, we get into some messy equations. And by the way, in antennas with antennas, in general, you're propagating electromagnetic energy in a very low loss environment, like free space or air. There's some, but not much attenuation. Now I come down to this, so how do I get E? Well, you remember the old curl of H was equal to, in general, it was J plus the partial of D with respect to T. But I'm going to do it in the phasor domain, the way I think everybody we're going to work in the phasor domain unless we need to go to the actual time domain for transients. So if the curl of H was sigma E, I'm just going to drop that, plus the partial of D with respect to T, and when I do the necessary adjustments by putting D as epsilon E, and going to the phasor domain, I get J omega, right? And then it's going to be epsilon E, correct? Are you with me? Just watch. It's more important that you see. I'm just doing it. What am I really after? I'm after E, right? I've made no gross assumptions we're in the far field yet or anything. So now I can say that E here from that equation is actually going to be equal to 1 over J omega epsilon, right, times the curl of H. Here I want to ask the class, remember I want just E. What do you think I'm going to do next? Anybody? Based on what I've done in the past. Anybody? Jack, Jake, Jack, William, Jack, Tyler? Huh?
Divergence.
Well, divergence of E?
Could you
Let me just mention something. He said something that's kind of interesting. Well, divergence of E is charge density, isn't it? Remember I said it was lossless, right? What's the divergence of a curl? Anybody remember? 0. The curl of a divergence and divergence of a curl is 0, isn't it? Right? So maybe that's not, I don't need 0. What do I need? Well, what if I take H there and replace it by this? Then I have curl of A, don't I? You're on the right track. You're trying to fuss with this one. So if I go ahead and I put this equation for H, now I get this. I get 1 over J omega epsilon mu, right? because there's epsilon down there already. And then I get curl of A. Now, I've done something like this before. I just want to mention it. This is not new to you. Do you remember me doing the curl or something? Of E? And I did something funny, too. Then I took that curl, and I said, because I had vector calculus long ago, but I use it all the time, I know an identity. I know that's equal to the gradient of divergence of A minus del squared of A. Now, you don't have to remember that one. You're going to see it's very useful if you go to grad school especially. So I know now that E is equal to, right here, 1 over j omega mu epsilon, and then it's going to be gradient divergence of A minus del squared of A. This is called a Laplacian, but it is a vector Laplacian. Now you got to be careful about vector Laplacians, because that is not just del squared of ax plus, in Cartesian it's del squared of the ax component, ax plus del squared, in the back of the book he shows us del squared of the ay component, ay times del squared of az. It's not. In spherical and Cartesian coordinates, Dr. Wentworth's book does not show you the del squared operator in either of those coordinate systems. I will give you that for completeness. Now, that's the world I live in when I do transient nonlinear stuff. I have to do this kind of stuff if I'm doing closed form solutions. So that's a vector Laplacian. Now, here's the thing. When I look at this, I got E here. But here's what E is actually equal to. Remember I said that H, these are the two coupling equations, is equal to that. Remember that in terms of A? E itself is actually equal to minus the gradient of the voltage. Remember, that's electrostatics, isn't it? If you had a fixed charge, it would be that. And then it's minus dA dt, if it's time domain. Or if it's frequency domain, it's minus gradient of voltage minus j omega A here. And I don't know where Wentworth has this. He shows B. He actually doesn't show that. So, put a star on this one. I'm going to have to come back to that in a little bit and explain it more. But anyway, we have E and H. Now I'm going to show you something. I'm going to go over here, and I'm going to set this equal to minus the gradient of the voltage minus j omega times A. And now I'm going to show you something. What they usually do is this, and this is called, how many have heard of gauge conditions? Anybody? Have you ever heard of a gauge condition? It's something that's going to, if you have a set of solutions that has a constant involved, like when you solve a differential equation, you get a solution that's a function of the dependent variable, space-time, plus a constant if you don't have hard limits. Do you all know that? Well, the gauge condition is like that constant, and that's the important thing. So if you take a look at this right here, what they're going to do is set this right there equal to this, including this. So they say 1 over j omega mu epsilon, right there, times the gradient of the divergence of A is equal to minus the gradient of V. Y'all follow me when I did that? I simply equated the volt. Maybe I should use a different color. I equated this voltage with this component, and I have to include this constant front. That's what I ended up doing. This is called a gauge condition. And I'll write it down. You don't have to know this, but it's important to see, at least get some perspective. So when I see this, here's what happens next. We're assuming we're in an environment that does not change spatially. And if it doesn't change spatially, please listen to me just listen. And what I can do is this. And I can put a minus sign over here. And now I have the voltage in terms of A. Y'all follow me? That's called a gauge condition. You don't have to worry about that. And when I go through that, if I use that gauge, then I can equate this to this, and I end up getting this. I have del squared of A right there. And when I go through this to that, take it, then it's going to be plus omega squared mu epsilon times A. That itself will be equal to 0 in free space. Do y'all follow me in this? I'm going to stop here. You're probably getting a little tired of this until you see it apply. The reason this is an important equation, it usually is set equal to an impulse function over here that's only going to turn on at the origin where the current is. But the reason this is so important, that looks a lot like del squared of E, doesn't it? Here we're going to be in Cartesian, or I mean spherical coordinates. The nice thing about this, that magnetic vector potential has only a vertical component. If you have currents in that direction, this is real important. It doesn't have 3 components. And it's also fairly easy to solve for. Now, this is a little advanced. Dr. Wentworth does not do that. But now I'm going to get to the crux of the problem. You have to understand this, that normally what we do is assume a current distribution. We get A. Once we have A, we get H. Once we have H, we get E. That's the general progression. What Dr. Wentworth's book does, and I don't blame him for this, is kind of circumvent a lot of this. On page 442, he goes through what I just did, and he goes from a Cartesian or cylindrical system and does a transform into spherical in equation 8.44. If you write that down, that's just going cylindrical to spherical. It's just doing this. Then after he does that, he literally takes the curl of A and he gets equation 8.45. Now the reason I'm not doing all this is because we don't do that. I don't ask you to do that. You all hear me? Then after he has that, ultimately he gets the E field the same way I would do, but he does one other thing. And I'm going to talk about that. He says, let's just talk about far field. We don't want to deal with near field. We can get the exact equations for near field. And if you write this down, the near field equations, if you need them, are equations 8.45, if from a spinning wire current, thin piece of current, 8.45, 8.46, and 8.49, or sorry, 8.46 and 8.47. I'm going to write down, and I'm going to do it according to what he has down here. This is now going to start making a little more sense. And it's going to be directly applied, and you'll see why. And once you read through this section, you're going to see why I did this so, I might say, nonchalantly and not really worry about a lot of the details, because this stuff is outside the scope of this class to really get into this. If you're interested in this, you can take a physics course from Jackson. It's a great book that's taught over there, or you can take the Advanced Electromagnetics course here, and that's really a doctoral course. The master students can jump in, and I'll be happy to teach that if we get enough kids. And I love this stuff, but I know you'll be well outside your realm. You don't understand spherical Bessel functions or Legendre polynomials, I don't think. And that's kind of you gotta know that. I can teach that, but I can't teach it in this class. So let me get to this. In general, we have a thin wire, a thin piece of antenna. We have IDL. Wentworth uses this. From that, we get A. I'm going to just put this down. We get the differential A field. Don't worry about this. Just listen. This is going to be mu 0 over 4 pi here. Then I'm going to have I naught here. I'm going to have e to the minus j beta r. R is the distance. It's divided by, you can put magnitude R here. A lot of times they do to show there's no vector sense there. It's magnitude. Then it's going to be times dl, and I'll do it Wentworth's way. Where Dr. Wentworth has a vector sense over there. So if it was a differential in the z direction, it would be dz az. That's what that vector sign means, okay? He has that. That's the differential A field. Once I have that, I get total A by integrating dA, just like you would integrate over a source of current. Here you would integrate over, a source of charge to get voltage. Here you would integrate over the source of current to get A total. All right, it's not hard to do, but it can be a little nutty. So now I get A. Once I get A, I get H. And here I'm going to show you what it is. And this is going to assume this. We're assuming that this particular antenna is going to be a length L. Maybe I better draw it over here. So I'm going to assume I have an antenna with a current I naught on it. And the length of the antenna is L. And it's actually in the z direction. And I'm going to assume I have a vector R pointing out to a position. And this angle, since this is the z-axis, will be theta. And from here, I can get A by taking this equation, this is nice, and just multiplying it by L, replacing dl by L. And here's why. And Wentworth's book says he's going to assume at this point, this is important, if we assume a short dipole, what does that mean? I always used to ask this stuff. Whenever I hear somebody, we'll assume it's small. What's small? Give me an idea. You ever hear that from mathematics? I mean, when you take math, don't they say if 1 plus x where x is small? Well, what's small? Usually the rule of thumb is a tenth of whatever value is next to it. Like if it's 1 plus x, x would be a tenth or less. That's a rule of thumb, but it's not always that way. So when we take a short dipole, we assume L is less than the wavelength in free space over 10. That's the assumption for a short dipole. Got it? It's also the assumption for a short wire. If you remember with transmission lines, if you had a wire longer than the tenth of a wavelength, then you had to use transmission line equations to get the impedance. If it was less than that, we just say it's going to be a piece of wire. If it's a short dipole, then you can say that A, and A would be in this direction, that current's going up. A here would just be equal to mu 0 over 4 pi I naught, whatever the current is there, e to the minus j beta r over the magnitude of r, and then it would be times L. And that's A in a nutshell, because if we did the differential integration, because it's short, there is no appreciable wavelength distance from the bottom to the top there when you do the integration, so there is no phase change in the information from here to here. We also assume one other thing. We assume R here is much, much greater right there than L. So we're far length from the antenna. If we don't do that, we get into some trouble. They're assuming you're a fair distance from the antenna. Now, frankly, if you're not a fair distance from the antenna, you got bigger problems. I'm just leveling with you. Because whenever you get close to antennas, you change the impedance of the antenna. The driving point impedance that it sees, from the source sees, you change the current distribution. Everything I'm doing is now thrown out the window because it won't work. But if we assume this and this right here, and I didn't put a vector sense, I'm going to put AZ here. Usually Wentworth would just put a vector over L to say that's the vector sense. But really it should just be A sub L to give an indication of a unit vector in the direction of the current. With me? No matter how you say it. Once I get A, I go ahead and I do a spherical transform. So I say AZ here, and he'll have it in the book. If you remember, if this is AZ and you had spherical coordinates, you'll have a radial coordinate AR, And then you'll have a coordinate this way that's going to be a theta, right? And if you remember right there, since this is theta right there. And when we look at this, AZ itself here would have a projection in the R direction as cosine of theta AR, and then it's minus sine of theta A theta. And he'll have that, I'll tell you where his equation is. This is equation 84.44. Right above that, he has a transform, if you look. How many have their book here? Anybody? You got yours. Do you see it in there? It's 8.44, and it's right above the equation. He has AZ transform. So he'll do this. He'll take AZ here, and he'll put it here. Are you with me? And then this R becomes spherical R. He'll assume the antennas at the origin in a vertical direction. So and then what he'll do is take the curl of A. You could do this, but it's not really necessary. And when we do curl of A here, you get B, and what you'll have for that, B itself, actually, let me get H first, because it'll get rid of that mu 0. I know B is mu H, so what I'll do is get this, and that's going to be equal to J, right? I think the way he does it. He's going to have J beta L e to the minus J beta R, right there. It's going to be a sine of theta over 4 pi R, actually R, not R squared. And then it's going to be in the A phi direction here. And there's two ways to do this. He does it, he puts the R in, actually I'll do it this way first. He'll have 1 over R outside, and he'll have J beta plus 1 over R. So you have this, actually I put J beta there, I shouldn't. He'll have J beta plus 1 over R. Can you all see that, class, if you have your books? This is equation, is it 4.5 or 4.6? 4.5, I think, right? 8.45?
Yes.
All right, now what he's doing is he's doing the curl. And I can do the curl if I want to and take some class time, but this is what comes out of it. And the small r and large r are the same. Maybe I better go to small r's here because that's what his book has, I think. Is it, doesn't it?
Yes, it is small.
Now, here's the next thing he does. Just hear me. What he wants to do is compare apples to apples. So what he does here is when he looks at this, he's going to pull out, I believe, a J beta. Take a look at the book. And so it might be a J beta squared. When he pulls this out, he gets 1 here. All right? So he'll pull out a J beta. I think this is how he does it, but I don't remember. So he gets 1 here, right? And now I have to divide this by 1 over J beta, and there's an R there. I think that's how he does it, but I'm not sure. You might have a J beta squared. It doesn't matter. Are you all with me? By the way, this right here is a very important part. Now that's the general equation for H getting A, assuming A. There's one thing he's not including right here. He's not including any kind of a static charge buildup on the ends. And I want to just mention this. This is an ideal kind of thing. Because if you have current flow in a wire, and I need to tell you this so you understand it. If you just take a look at a wire antenna, you don't have to write this down, just listen. If I'm feeding it with a current I naught this way, then a current I naught that way is coming out of the bottom. It's called a differential feed. Does that make sense to everybody? With me on that? All right, current going in, coming out. All right, what actually happens is, if you looked at the magnitude of the current here versus distance, you would see it would start out at a peak, and even for very short dipoles, it'll start doing this. It has to go to 0 at the ends, because we know current distance is the constant value and stops, because then you get charge accumulation. You with me? Now, at this end and this end, there will be charge accumulation. they're not accounting for that, right? Because that's going to have a small effect on propagating fields. They're accounting for the effects that the time-varying current, actually the accelerated charge, has. The actual current distribution that he's talking about is this. And this is the most common, because he's assuming it's a differential current causing it, and it works when you do the actual integrations. He's assuming that over the distance that the wire is, the current has a value of I naught, like that, constant, right to the end it goes to 0, and there is no charge to worry about. You all with me on that? You don't have to worry too much about it. Just assume this is a very small chunk of the antenna and we only worry about the current. That's it. Now, if that's the case, everything I said works. But when we come to this point, we come to a very important point. Here is how we differentiate far field from an antenna. Write this down. When we talk about far field, have you heard that term, far field? Yep. Where did you hear it? Here? Anyplace else? All right, in general, here's the way I like to talk about this. Remember how I made this spiel about, I said a capacitor has electrostatic energy, but it collapses back, you can get it out. And I say if you have an inductor, it has magnetostatic energy, but when you put an inductor with current across a resistor, the resistor pulls out the energy, right? It goes to 0. All right, now, for a short wire antenna, there comes a point where you go literally from the near field energies to the far field energies. And the point is when this equals this. So for the far field, you have 1 is equal to 1 over J beta R. You drop the actual J, and you say then this distance R here is 1 over beta in magnitude. You all follow me? Now beta is what? Well, you know, beta times a wavelength is 2 pi, isn't it? Mm-hmm. So I could say beta is 2 pi over a wavelength, right? Right? Yeah. So you could say beta is 2 pi over a wavelength, or this. This is the point where the far field, how it's designated. You take lambda for dipole antennas. You say lambda, whatever lambda is, divide by 2 pi, that's the far field. Has anybody heard of that before? All right, some people. Now, yes, that works for a short wire antenna. Think about it logically. If I got an antenna and I'm at 300 megahertz, what's the wavelength? Short antenna, say this one. Wavelength would be what? C over F, right? 3 times 10 to the 8th over 3 times 10 to the 8th would be 1 meter, right? So for this short one, first, is it a lot less than a wavelength? Well, about, right? It's maybe a tenth. Y'all with me on this? So if I go a meter away from this, and after that I can pretty much ignore near field terms. Keep going in frequency though. Instead of having 300 megahertz, make it 3 gigahertz. Now what's the wavelength? It's not 1 meter, it's 10 centimeters, isn't it? Now this becomes of the length of the wavelength. You with me? Now my analysis doesn't hold true, and also the far field would be a tenth of a wavelength. I mean, sorry, 10 centimeters away. Y'all with me? Sorry, it'd be lambda. Sorry, I said a meter. It would be lambda, which would be 1 meter over 2 pi. What is that? That's about 1/6 of a meter away. So it's actually pretty close, even at 300 megahertz, right? What I'm really getting at is the near field, far field transition from a dipole antenna is very close. That's my point. You don't have to be a mile away. You'll find out for dish antennas, they're called aperture antennas, where you have not just a line of current, but you have a surface of current. It's much different. You have to be fairly far from that, and I'll get to that later. That's, yeah.
Can you remind me again what happens in near field, like what the difference is?
For antennas?
Yeah.
In the near field, the electric field is not dominated by the propagating field. So the field I calculate for the E, I've got H there, I'm going to calculate E in a second. This H field right here, that will change somewhat. Actually, the H field won't change for the near field. The E field will, because the electrostatic terms. So there you get terms that have to do with stored energy, and the field will be different. There's a way we deal with this is called impedance, near field impedance, that's much less, if I can get to it, I will. That's a more advanced topic. But for now, just realize, you know how you have a characteristic impedance in free space? There's a near field impedance that you have to work with, and that's a little advanced. We're not ready for that. So the bottom line is, this is the transition to the far field, right here. That's where it comes from. When you get this term and this term equated, because this term right here, the 1 over r, j beta r with an r there, is 1 over r squared. That is, in fact, related to near field energies. Okay? But it has to do with current, not electrostatic charge. Charge is voltage in E field from the charge. Okay, now let me get to the real bottom line. This you write down. So after I have that for H, let me just say this. I'm going to try to continue from this. That's H in general. What we do, we assume far field. When we assume far field, we get rid of this. Then you write it over here. You write this down. Put down short dipole. In general, H, you'll see this too in your book. And William or somebody with a book, or if you can tell me where this is, let me know. This is going to be for far field. This is the one we use. We get H itself, it'll be equal to beta, right? It's actually going to have a J in it. J beta, I naught, L, the length, e to the minus j beta r, times the sine of theta over 4 pi r. Let me put small r here because he has it in his book. I don't use that much because it looks like a V to me sometimes. And this would be in the A phi direction. Then when we get E, if we're in the far field, the only thing we do is say E is equal to eta times H in the far field magnitude and we say it's equal to J beta, or J eta beta, I think he has it, J eta naught beta L I naught e to the minus J beta, and small r right there, times the sine of theta over 4 pi small r and the A theta direction. And these are the two far field terms from a short dipole. And they're assuming they're pointing in the z direction. Let me just take a moment and mention some stuff about that. I'm over already. But we're assuming these dipoles are aligned on the z-axis. Do y'all follow me on that? Can anybody tell me what would happen? I mean, I look at that field pattern. I can take a look at the power pattern by just squaring this, right? And dividing it by 1/2 eta, right? Multiplying by 1/2 divided by 8 naught. That would be the propagating power density, wouldn't it, class? And we could actually plot that. It would be a sine squared. I'm going to do that next time. I'm going to go through, show you how to get the short dipole. I'm also going to do the half-wave dipole, the arbitrarily long dipole, and then the half-wave. I'm going to show you how to get gain and everything from this, but you're going to see it's fairly straightforward. I'm going to give you some homework to do. Come Wednesday, please do your homework. Maybe I'll even collect one just to give you something to force you to do it so you can come to class. And did y'all understand this lecture, what I was trying to get at? No. The reason I did that spiel on the potential is to give you perspective. I mean, when they just start writing down stuff where I was where you were, and they share, well, A vector potential stuff, they don't tell you you can't measure. They don't tell you why you're doing it.